Welcome to Empowered Learning. This is the third and final video of the video series on solving first-order ordinary differential equations by using substitution techniques. This video will specifically talk about Bernoulli equations, or first-order linear ODEs, where we use a radical or fractional exponent substitution to turn that particular equation from being what we're classifying it to be, which is a Bernoulli equation, back to what it was originally supposed to be, is a first order linear ODE. And so I'll explain in a second why I say that it should turn back to a first order linear ODE as it was originally supposed to be. So let's first define, let's first take a step back here and look at first order linear ODEs first. And let's see what that looks like and compare it to what a Bernoulli equation looks like so that we can see the similarities and differences. So recall that a first order linear ODE has this particular form here, okay? And of course, I'm choosing the standard form for it. Now, what if instead of having this type of equation here, we had something like r of x times y raised to some power here, okay? So let's say we had that. Now, of course, this looks very similar to a first order linear ODE, but of course it's not, because now over here I have a function of x and y, whereas for a first order linear ODE, I need just a function of x. So how would you solve that? Okay. Now, probably the first thing you're saying is, well, how could I actually neutralize this y raised to the n so that I could, essentially get rid of it? Okay. Or at the very least, make it look like something else that I could deal with. And so if you're thinking that, then you're actually thinking along the right lines of what we do to try to deal with an equation like this. Okay. So it turns out that if we make the right substitution for what that y raised to the n is, or whatever, or right substitution for y in general, then we can achieve what it is that we just talked about. So it turns out that Bernoulli equations are defined exactly like how I wrote up at the top of the page earlier, and here, Bernoulli equations are a specific type of first order linear ODE, but as I like to say, it has an identity crisis. And of course, that identity crisis is the fact that it's a first order linear ODE with a problem on the right side of its equation here. And so, of course, the substitution that we're going to do is to get rid of that. Now, for it to be a true Bernoulli equation, when we have this y raised to the n, n can pretty much be any real number except for 0 and 1, okay? Reason being, if n is equal to 0, then this is essentially 1, and now we have a first order linear again, okay? So nothing special about that. If n ends up equaling 1 in this case, then we have a situation where we just have rx times y, okay? So this exponent literally just goes away. And so now you see here you have on either side of the equation two expressions that both have a common factor of y, and you can move that all to one side, and then what you end up having is a separable equation in that sense. So that's why we're not really interested in the Bernoulli cases when n is equal to 0 or n is equal to 1 for that reason, okay? Now, for these Bernoulli equations, or as I like to call them, first order linear ODEs with an identity crisis, how we actually deal with them is we do the substitution that's prescribed here below, which is we let u be y raised to the 1 minus n, okay? And of course, if you think about it, if you have y raised to the n, and let's say we multiply this by y raised to the 1 minus n, then of course you literally just get y left here, okay? And in essence, that's kind of the motivation for actually making this kind of substitution here. But of course, we'll get a little deeper into the whole process and all that. But like I said, in general, that is the motivation for it. We're not going to use it exactly like that in our in these equations here, but again, that's the motivation for it. So in short, if we recognize that we have a Bernoulli equation that looks like this, then we want to make the substitution of u is equal to y raised to the 1 minus n. Okay, and of course, this is just all the different forms that we could write this particular equation in. Of course, our goal, just like we did in the other two videos, is once we do our substitution, the next thing that we want to do is solve for y. And I've done that and made it look in two different ways. And then from that, we would like to also figure out what dy over dx is. Because, of course, that's in our equation and we need to be able to substitute it. So in dealing with this type of equation here, it's pretty much the same thing. We get the prescribed substitution, figure out what y is, what dy over dx is. Everything is going to be written in terms of u and or x. And then from there, what we're going to see is that this type of equation with that substitution will essentially turn back into a first order linear ODE. And so once we have it in a first order linear ODE fashion, then of course we could use what we learned about first order linear ODE solving techniques to solve it. And the way that I'm going to do these problems is I'm going to use the formula way of actually solving them. And I introduced this way in the video that I had on solving first order linear ODEs. So if you did not watch it and you need to, you may want to do that first. All right. So once we actually solve this for u, then of course we know that u is going to be the same as y raised to the 1 divided by n. And hold on here. Yep, I think I may have said that wrong here. Yeah, so u is y raised to the 1 minus, yep, that's what I wrote wrong. Yep. So this is u is y raised to the 1 minus n. And of course, from that, we can solve for y by having y equal u raised to the 1 divided by 1 minus n. So here, whenever we solve this first order linear here, the first order linear equation will be in terms of u. And then, of course, from that, we just do what we need to solve for y. All right, so in a nutshell, that's pretty much it about Bernoulli equations as far as talking about the concept behind it. We just need to do some practice problems now. But before we do that, let's just summarize everything that we need to do here so that we kind of have everything in one spot. It may be good for you to actually take or write some of this down if need be, or take a picture of it or whatever, just to have it handy, just in case you forget some of these steps. But I guarantee you, if you do enough of these problems, you'll remember. So, of course, step 0, and this is just for the constant solutions here. If our value of n that we extract out of our Bernoulli equation ends up being greater than 0, then y equals 0 for all values of x will always be a constant solution. Okay, so that is a given. After that, of course, we recognize that we actually have the Bernoulli equation in this form, and whatever numbers on the exponent for y, that's what our n is. We do this substitution, rewrite y in terms of u, and then find dy over dx, whatever that's going to look like. Afterwards, we take our dy over dx and y and substitute it back into our equations here. And then from that, we will end up having a first order linear ODE, but it will be in terms of u. And so then from there, we solve our equation for u, noting that h is integral of p dx, and both p and r are functions of x. And then, of course, we just use this equation here to figure out what y actually is. And that's pretty much in a nutshell the procedure. All right, so let's look at an example that I've worked out first, just to kind of get the flow of this problem. So we see here that we have a first order equation here, and it looks like it's first order linear. However, we see that we have y squared here, so it can't be first order linear. Because I have y raised to some power here, we know that it's going to be Bernoulli. Okay, so that's how we know. So looking at this, the first thing that we see is that this is a 2, so that means n is going to be equal to 2. Okay. Now, since n is equal to 2, which is greater than 0, then that also tells me that y equals 0 is going to be a constant solution to this particular equation. Okay. Now, if we look at this equation that we were given, if I rewrite it like this, then of course, and I'm just doing the lines over here to make it look different than what I've had before. Nothing special about what the lines mean. So here I know that my p of x function is just going to be x, and my r of x function is going to be x as well. Okay, and n is 2. So here we allow the substitution for u to be y raised to the 1 minus n, and of course, since n is 2, then that means u is equal to y raised to the negative 1, or u is equal to 1 divided by y, which means y is 1 divided by u. Okay. And of course, now that we have y written in terms of u, we can figure out what dy over dx is. And in this sense, notice that u and x aren't the same variable, so we are going to have to employ the chain rule. Because remember, u is assumed to be a function of x, even though it's not explicitly stated. So when we look here, we take the derivative of u raised to the negative 1 with respect to x. It's just going to be like we're taking the derivative of u raised to the negative 1 with respect to u, which is what this is, times derivative of u with respect to x. And of course, we see that dy over dx just ends up being a negative 1 over u squared times du over dx. So now we have what dy over dx looks like. We have what y looks like. And so we can substitute all that information into our first order ODE here. So y prime of dy over dx is all this business here. Y is just 1 over u, which is what we see here. And of course, y squared is just going to be 1 over u squared. And if we clean all that up, looks like this. Now, from this point, we know that this particular equation is going to be a first order linear ODE. It's just that it's not looking like it yet because we don't have this du over dx by itself. So to do that, we're going to multiply both sides of this equation by negative u squared, or just u squared rather, here. But actually I did negative u squared. I just did it in 2 steps instead of 1. So if I multiply by u squared first here, then I end up getting just minus du over dx, and this is u times x, and then I have x over here. But then if I multiply everything by negative 1, then of course I get what you're looking at here. Okay, so I guess I'll just go ahead and write in the negatives here because that's really what I did. So from here, in this form now, we see that we have a first order linear ODE. And notice that in this form, my p is going to be minus x, r is going to be minus x as well. Now, if you notice, I had to look at it in this form, and this is one of the reasons why I put the lines over the p of x and r of x, just to distinguish, hey, I'm talking about Bernoulli equation here, versus here I'm talking about first order linear. Okay. So now that I have that, notice that everything is in terms of u. So I'm going to substitute in everything I need here, my P and my R, into this formula here, where H is going to be integral of P dx. And so, of course, here, our P is just equal to minus X. So we take the antiderivative of minus X is minus X squared over 2. Substitute that back in, E raised to the negative H. That's just going to be E raised to the positive X squared over 2. E raised to the H is just E raised to the negative 1/2 X squared times a minus X dx. And then, of course, here we see that we can use substitution rule to evaluate this indefinite integral. So we do the substitution here. Let Z, and I'm not using W or U this time because I need something to look a little different. So that's why I use Z. So Z is equal to negative 1/2 X squared. So that means DZ is negative X dx. And so, of course, that's exactly what I need here. So I can rewrite this integral here in terms of Z now. So that's exactly what I do here. Everything else pretty much stays the same. Of course, the antiderivative of E to the Z with respect to Z is just E to the Z. And then Z, of course, is negative 1/2 X squared. So we put that all in. So from this point, I go ahead and I distribute the E raised to the 1/2 X squared over 2 to both terms. And notice here that I end up getting just 1 plus C times E raised to the X squared divided by 2. And from here, remember that our U is the same as 1 over Y, okay? In other words, Y is 1 over U, okay? And so for here, I know that because, and I'll go ahead and write this in, that U is the same as 1 over Y, then that means Y is the same as 1 over U. And so that's why Y's end up being 1 divided by 1 plus C E raised to the X squared divided by 2. And of course, finally, like how I said before, since N is equal to 2, which is greater than 0, we have a constant solution of Y equals 0. And so these are our solutions to our differential equation here, our Bernoulli equation here. All right, so let's move to the next example. All right, so for this equation, right off the bat, we can tell that is a Bernoulli equation because it looks just like a linear one, except for we have this Y raised to the 1/3 here. So from here, we know N is equal to 1/3, which is greater than 0. And of course, that lets us know here that Y of X equals to 0 for all X in the real numbers is a constant solution here. So this is just a fancy way of saying that Y equals 0 is a constant solution. So we'll keep that in mind and just carry that on and tack that on to the answer at the end if we actually find any non-constant solutions. So at this point, we know what our N is. So here, since this is a Bernoulli, we know that we're going to let U equal Y raised to the 1 minus N, which in this case, this will be Y raised to the 2/3. So if that's the case, then we need to figure out what Y is. So to figure out what Y is, we would raise each side to the 3/2 power here. And that would make Y equal to U raised to the 3/2. So now that we know what Y looks like, we also need to figure out what dy over dx looks like. And remember here that what Y is written in terms of U, and since these variables don't match, we have to utilize the chain rule. So chain rule here says we take the derivative of this like it's with respect to U, and then we multiply it times the inside function, which is U, multiply times derivative of U with respect to X. And so this is what our dy over dx looks like, which is the same as y prime. And I'm just writing that because we see it here. So therefore, we have everything that we need. So y prime minus 3 divided by xy equals x to the fourth, y raised to the 1/3. All we have to do is substitute everything in. So our y prime is 3 over 2 u raised to the positive 1/2 du over dx minus, we have 3 over x. And of course, our y is u raised to the 3 over 2 equals x to the fourth times y, which is u raised to the 3 over 2, all that raised to the 1/3. So once we do that, then of course, we can do some more simplification here. What we see here, this is just going to be u raised to the 1/2. And so what I can do to both sides of this equation here to get du over dx by itself is I can multiply both sides by 2/3 times u raised to the negative 1/2. Okay. And if I do that, that would basically transform what I currently have as an equation into something that looks like a first order linear, like what I'm looking for. Okay. And of course, from that, our first term here, of course, 3 over 2, 2 over 3, those are reciprocals of each other, so it's just 1. U raised to the negative 1/2 times u raised to the positive 1/2, reciprocals of each other, so it's just 1. So we just have du over dx in the first term. For the second term, we have 2/3 times 3 over x, which is going to be the same as a minus 2 over x. We also have u raised to the negative 1/2 times u raised to the positive 3/2, which is the same as u raised to the 2 halves, which is just u raised to the 1. So this is just u. And on the right side, of course, u raised to the 1/2 times u raised to the negative 1/2 is just 1. And all we're left with is 2/3 x raised to the 4. And so this is first order linear. And so now we see that this first order linear ODE is in terms of u, so we need to solve for u. So therefore, u is going to be e raised to the negative h times integral of e raised to the positive h times r times dx plus integration constant. H is integral of p dx. And notice here that our p is going to be a minus 2 over x, and our r here is 2/3 x raised to the 4. All right, so now we will go ahead and find what h is going to be. So h is integral of p minus 2 over x dx, which is just going to be a negative 2 times natural log absolute value of x, or natural log absolute value of x raised to the negative 2. Thus, this means that e raised to the h is going to be e raised to the natural log of absolute value of x raised to the negative 2, which is just absolute value of x raised to the negative 2. And since x raised to the negative 2 will always be a non-negative number, we could just drop the absolute value signs. Okay. this also means that e raised to the negative h here is just going to be x squared. All right, so now we just find out what u is. So we have u is equal to x squared integral of times integral of x raised to the negative 2 times r, which is 2/3 x raised to the 4 times dx plus c. And this is essentially just x squared times 2/3 integral of x squared dx plus c. And here all we need to do is just integrate x squared, which is going to be 1/3 x cubed. So u just ends up being x squared 2/3 times 1/3 x cubed plus c. And this ends up being 2/9 x raised to the 5th plus c x squared. And so this is what our solution for u would be. But what we need now is to figure out what y is. And so if you remember, if we go back up here, we said that y was actually going to be u raised to the 3/2. Okay. So since I know what u is, y is just u raised to the 3/2, which is all this business here, raised to the 3/2. And so that would be our final answer here, along with the fact that y equals 0 is a constant solution here. So take that and put those two things together, and this will be our final answer. All right, let's move on to the next example. Okay, so for this example, we have a Bernoulli equation, but we also have an initial condition. So this is going to be an initial value problem. Okay. So first things first, we do recognize that it is a Bernoulli equation. So this is our n. Since n, which is equal to 5, is greater than 0, this means that y equals 0 is going to be a constant solution here. Okay. So now what we need to do is use our suggested substitutions here. So we say we're going to let u equal y raised to the 1 minus n. And since n is 5, that would mean that y raised to the negative 4 is going to be what u is. So therefore, to figure out what y is going to be, we have to raise this to the negative 1/4 power on both sides. And so this essentially means that y is going to be u raised to the negative 1/4. So now that we know what y is, we also need to figure out what dy over dx is. And again, remember that y is in terms of u. And since these two variables don't match, we have to use the chain rule. And that will be negative 1/4. And of course, we have to subtract 1 here, which is like another minus 4/4, which is minus 5/4. And then we multiply that times the derivative of the inside function, which is just u with respect to x. So of course, I'll just rewrite this to make sure that it's clear. dy over dx is just negative 1/4 u raised to the negative 5/4 times du over dx. So we have what dy over dx is. We have what y is. So now we just take our equation here and we make our substitutions. So here y prime plus 2 over xy equals minus x raised to the 9 times y to the 5th. We do our substitutions. Y prime, which is the same as dy over dx, is just a negative 1/4. Of course, u raised to the negative 5/4 times du over dx. And so if my pen would work right, I could write it really fast. All right, so we have that for the first term. Second term is just 2 divided by x times whatever y is, which is y raised to the negative 1/4. And then that equals negative x raised to the 9 times u y raised to the negative 1/4. And all that raised to 5. And of course, that could just be rewritten as u raised to the negative 5/4. And so I'll go ahead and write it like that just for simplicity. Okay, so now that we have this, our goal here to get this in the first order linear form is to get du over dx by itself. So that means I have to multiply both sides of the equation by the reciprocal of this particular term here. So for us, what that means is I'm going to multiply both sides by a negative 4 times u raised to the negative 4/5. Okay. So I'm going to have negative 4 u raised to the negative 4/5. Then we'll, of course, multiply that to the second term as well. And we also need to multiply it by the other side as well. All right. So now that we have all that written, of course, the first term, we know that that's just going to be du over dx. Negative 4 times negative 1/4 is 1. And let's see. Oh, yeah, that's not right. This should be a positive 5/4, not negative 4/5. Yep. I'm trying to multiply when I... Yep, that's not right. So this should be positive 5/4. And same deal over here. All right, so yeah, so now we will multiply u raised to the 5/4 times u raised to the negative 5/4. Of course, we add the exponents, turns to 0. U raised to 0 is 1. So that's why this first term ends up being that. Plus 2 divided by x. We multiply negative 4 times 2. We get minus 8. So here, so it'd be a minus 8. And u raised to the 5 over 4 times u raised to the negative 1 over 4 is u raised to the 4 over 4, which is just u. And then, of course, on the right-hand side, we know that the u raised to the negative 5 over 4, u raised to the positive 5 over 4, that will multiply together to be 1. So all we have is the negative 4 and the negative x raised to the 9, which would be a positive 4x raised to the 9. And this is first order linear. So now that we have that, and we see that our equation is written in terms of u, then we just solve for u. So this would be e raised to the minus h integral e raised to the h times r times dx plus c, where h is integral of p dx. And of course, here again, we see that our p is a negative 8 over x. Our r is 4x raised to the 9. And I'll just go ahead here and figure out what h is. This is just a minus 8 natural log of absolute value of x, which, of course, this negative 8 could be put back into the exponent here. And since x raised to the positive or negative 8 would always be a non-negative number here, we can drop the absolute value signs. Yeah, pen doesn't want to work for me today. All right, so that has to be good enough for now. All right, so now that we have that, then of course that means e raised to the h is going to be e raised to the natural log of x raised to the negative 8, which is just x raised to the negative 8. And e raised to the minus h will just be x raised to the positive 8. So u is equal to x raised to the 8 times integral of x raised to the negative 8 times r, which is 4 times x raised to the 9 times dx plus c. And this will just be x raised to the 8 times integral, well, times, we need to factor out that 4 first. All right, so we'll factor out that 4, and then x raised to the negative 8 times x raised to the positive 9 is just x raised to 1, which is just x, plus c. And this will just be 4 times, integral here will be x squared divided by 2 plus c. Of course, from here, this means that u is essentially 2x raised to the 10, because of course x to the 8th, x to the 2 is x raised to the 10. 4 divided by 2 is 2. And then of course x raised to the 8 is going to be multiplied times the integration constant as well. And so that is what u is. Of course, we can come back up here, remember what y actually is. So y is u raised to the negative 1/4. So since u is this, y is u raised to the negative 1/4, which is essentially going to be everything that we have here raised to the negative 1/4. And so this is our general non-constant solution. And what we'll do now is actually use our initial condition here to figure out what our integration constant is going to be. So we'll come here, we'll apply the initial condition, and that was that y of -1 is equal to 2. And of course, that means whenever we let x equals -1, let y be 2. So here, y, I'm going to say that's 2, equals, and then all this business here, 2 times -1 raised to the 10 plus c times -1 raised to the 8, all that raised to the -1/4. So we have 2, which is equal to -1 raised to the 10 is just 1 times 2, which is 2, plus -1 raised to the 8 is still 1. 1 times c is c. All that raised to the -1/4. And so now we just need to solve this. So here what we can do is raise both sides to the -4 power. So I'll do this, -4 power, -4 power. Then 2 raised to the -4 is the same as 1/16. And over here, these two multiply together to be 1. So I just have 2 plus c. And then, of course, c would just end up being 1/16 minus 2. And, of course, 2, we could rewrite that as 32/16. And that ends up being a minus 31/16. So c minus 31/16. So now that we have all that in place, then we can finally state what our final answer is. So final answer, or answers. Of course, we said way up here at the top that y equals 0 is a constant solution. Yeah, it looks horrible. All right, I tried to make it look better. All right, y equals 0. And of course here, this was our answer here. Y is equal to 2x raised to the 10 minus 31/16 x raised to the 8, and all that raised to the -1/4. And so that is final answer here. Of course, I could try to simplify that a little bit more. Don't know if it's worth it for you to do that, but it is possible to do it that way. For those of you that are interested in seeing what that actually looks like, I'll go ahead and do it. For those of you that are not interested and you're fine with this answer, you can go ahead and stop this video now. All right, so if you want to simplify this a little bit more, then here, just notice that this is the same thing as 1/4 root of 2x raised to the 10 minus 31/16 x raised to the 8. And notice here that we have two groups of x raised to the 4s in both of these terms here. So in other words, I can factor out an x raised to the 8 out of both of these. So if that's the case, I have x raised to the 8 2x squared minus 31 over 16. And of course, we could split this up here. Didn't quite go the way I wanted it to go there. So here we could split up this as the fourth root of x raised to the 8 times the fourth root of 2x squared minus 31 over 16. So we could do that. If I did that, then the fourth root of x raised to the 8 is just x squared. And then we have 2x squared minus 31 over 16 here. And so this is what it would look like if we simplified it. Now, of course, if you didn't like this fraction here, you could go a little further if you wanted. And I'll go ahead and show you what that looks like if you wanted to go a little bit further. All right, so if you want to go just a little bit further, then just know here that we could rewrite this 2x squared as 32x squared over 16. And if we did that here, so 32x squared, it'll be minus 31. And then this will be the same as square root of 16 here. And of course, square root of 16, this is just 4. And so I have 1 divided by 1 divided by 4. And that would just be 4 over x squared. And this will be 32 square root of 32x squared minus 31. Okay. So from here, depending upon how you're actually going to use this answer, you could use this form. You could use this form. Or you could keep it in this form for the non-constant solution. All right, so I do have one more example that we need to cover here. So I'm going to go ahead and cover that. I believe it's one I've already worked out, so I'll be able to talk through it relatively quickly. But another Bernoulli equation example here just to round us out. All right, so for our last and final example here, we see that we have another Bernoulli equation. What's different now is that, of course, the exponent is not explicitly given to us. So you got to know that square root of y here is just y raised to the 1/2. And of course, n is going to be, of course, this is y raised to the 1/2. And from that, n is going to be equal to 1/2. And again, since that's greater than 0, then it means we have constant solution at y equals 0 here. And of course, that's what I mentioned here. So from that, kind of the same thing we've been doing before. Let u equal y raised to the 1 minus n. And since n is 1/2, then that means y raised to the 1/2 is equal to u. So that means that y is equal to u squared whenever we basically square both sides here to get y on its own. Now, when we take the derivative of y with respect to x, of course, that's like taking the derivative of u squared with respect to x. U and x don't match, so we have to use the chain rule. And that's how we get the dy over dx is 2u times du over dx. Once we're there, then of course we just need to substitute what dy over dx is and what y is into our Bernoulli equation. So with y prime, do the replacement. With y, do the replacement. And of course, y raised to the 1/2, that would be the same as u squared raised to the 1/2, which is just u. So from there, we divide both sides of our equation here by 2u so that we can get du over dx by itself. And if we do that, we end up with this result of du over dx plus 1/2 x times u equals 3x. And so we see that in this form, it is first order linear. And we identified our p as being 1/2 x and our r as being 3x. And then, of course, from here, we use the formula that I've been using to solve first order linear ODEs. Of course, this is the formula. We know h is just integral of p dx. And let's not forget here that in doing this, the e raised to the h, that is the integrating factor. And of course, the purpose of the integrating factor is to find something to multiply by both sides of our linear ODE here that will allow us to be able to essentially turn it into a separable equation. And so what this formula here is a result of that happening. So from here, we go ahead and let p be 1/2 x, take the antiderivative of that, ends up being x squared divided by 4. So we substitute that in here, e raised to the negative h, e raised to the positive h, and we see here for our integral that our integrand is one where we can actually use the substitution rule to be able to find out what the integral is. So you see that from here we choose to have 1/4 of x squared be w, and then of course we take the derivative of w with respect to x and rewrite everything in a way so that we can replace what we need. So here we see that 3x dx is the same as 6 times dw. And after we do all the work, go ahead and substitute all that stuff in. Once we do that, then of course we do all the work here. Once we get to this point, then this is just a constant which we pull out. Integral of e to the w with respect to w is just e to the w. So that's why we see that there. And then we distribute the e raised to the negative x squared divided by 4 to both terms. So I went ahead and substituted in w first, and then I did that. So that's what we have here. And then because of the fact that u squared is equal to y, we got u, so y is just going to be that squared. So we just take all that and we just square it. And of course, our final answers again is just what y of x is that we found here, as well as our constant solution of y is equal to 0. And so this concludes the example in the video series on solving first order ODEs by using substitution techniques. I hope that this helped to clear things up, and I hope that the myriad of examples gave you a good idea of the kind of stuff that you should see. Take care.